And today's talk is going to be about securing your daemons using systemd, so about using the feature that systemd provides to protect a service from the outside and to protect the rest of the system and the network from the service itself. So, as an introduction, why would we use systemd to do this stuff? This is something I want to cover before actually I talk about any of the features. So, nothing that I'm going to be talking about today is in any way new. You can do everything using tools and code in the service itself, but there is advantages to doing it in systemd. So, well, the first one is that we try to make it as easy as possible. I mean, I think it's easier to type some configuration commands in a unit file than to add code to the daemon itself. But then there are also implementation advantages. So the implementation in systemd is pretty complex, but it's only done once, so it's in the long run it's better than doing it in every service. Systemd makes an effort to abstract hardware differences, kernel versions, kernel compilation options, and so on. And there's a caveat here that when systemd, for example, is running on a CPU that does not support some feature, or the support for this feature for this CPU hasn't been implemented yet, it will quietly just skip this certain protections and continue. So those protections should be understood as stuff that you add on top of other protections, not as the only thing you do to confine your service. And the last technical advantage I've listed here is that doing many of those things requires privileged operations, so basically required root rights. So the traditional way that this was done was that you would start a service as root, it would do some configuration operations, I don't know, some confinement operations, or maybe even opening of sockets, creation of files, and then it would transition to a user. But it's kind of nice to run a service completely as an unprivileged user, but you cannot have both. So, moving the preparation operations to systemd kind of give you best of the both worlds, because systemd is doing the parts that require privileges, and then starts the service itself as the target user. And also, you don't end up in this situation where you mess up something in the service and it runs as unconfined root, right? Is anyone here who does not know what systemd is or what unit files are? Okay. So services in systemd are started by through text files that describe what should be started, and so those two lines are a minimal service to start a single daemon, and then additional options I'll be talking about today would be added here. And then to actually start the daemon, you call systemctl start my daemon service, and so that's one way to do it. I mean, if I wanted to do some debugging, I might start the service from the command line, but of course then it runs as part of of my user session, and it's not part of it's not part of systemd, so that's not good. And there's a middle ground. It's systemd run. Who knows about systemd run? Who uses systemd run? Okay, a few people. So basically, this line is more or less equivalent to this one, except that there is no unit that is created on disk. There is like a temporary unit file that is created for the duration of the service, but actually it is still systemd, so process number 1, which is starting the service. The service is still run as its own part of the process tree. It's not part of the user session. But the syntax is more convenient for testing things. And then this last option with systemd run with -t. I'll be using this today to show some things. It just connects the T is short for terminal. It connects the input and output of the daemon to my terminal session. So instead of all the input the input connected to the null and the output going to the logs, the input and output are connected to my session, so I can do some printing and debugging and so on. Okay, so that was like the intro. So the first security primitive. So the cornerstone of Unix security is user separation. I mean, everybody should be using it. It's very simple. Everybody knows about it. It's very it's actually very good separation of daemons. But we don't on Linux we actually don't use it as much as we should. So, for example, on Android, every application gets its own user. Why aren't we doing this on Linux? Well, because it's kind of hard. So the way that this works under systemd is basically that you specify user equals something, and then the service runs as the specified user. And of course, usually I'm doing systemd run for debugging, but the same part would go in the unit file. So by default, you get root with all privileges, and then you override the user, and then you get a different user. And there's a systemd run switch to do it without, in slightly shorter form. Okay, so if you are packaging a daemon or writing a daemon of your own, please use a separate user for it. Okay, so we have our daemon, and the daemons usually should not have access to the file system. So I don't know, if we are running a web server, chances are that it should be serving some files from /var/web, not from /home ever. So there's those two high-level options. Protect home equals yes means that the service does not see home. So this is implemented through mount namespaces. So this is taking systemd is taking a functionality that the kernel provides and has been providing for a long time. It just makes it very easy to use. In this case, it creates a mount namespace for the service, and then in this mount namespace mounts an empty directory over /home. So /home appears empty, and then there's another variant called protect home equals read only. And also, let's say you have a backup service and it actually needs access to the files. So you want it to be able to access home, but not to modify anything. I should mention that those read-only in this case, it's an additional protection on top of the normal access mode. So if the daemon does not have privileges to write to the file, it is not able to write to the file. But if it had, the access mode would allow it to write to the file. But this part was mounted as read-only, then it can see the file but not write to it, and so this is like an additional thing on top of the other protections. So on top of user separation. And the protect system equals yes is about making /user and similar stuff read-only, and then there are like variants of this. So protect system equals full also makes etc/etc read only, and then protect system equals strict makes everything read only. And if you want the and makes /etc empty, and then if you want the service to access some files, you add them back through kind of lower level options. So those lower level options are those three. I mean, you might guess what they do. So inaccessible paths hide stuff, and read-only paths make parts of the file system tree read-only. And the last one, read-write paths, is about adding stuff back in a way to the file system tree that the service sees in a way that it can write to it. And there's many variants of this. Bind paths is about doing all the stuff that I was talking about, but moving parts of the file system to a different location. Yes?
When you use protect home, then process see /home as a empty view, yeah?
Yes.
What about its own home view?
Yeah, it also does not see its home view.
Okay.
I'm pretty sure. So the question was whether protect home applies to the home directory of the user. So, I mean, this is mostly used for system daemons which have homes outside of /home, right?
Okay.
So this is about some kind of static operations on the file system tree. There's a pretty specialized option, but it's very useful. It's private TMP equals yes. So by default, all users and services use the same shared /tmp and /var/tmp directories. And of course, every once in a while it happens that some daemon creates a file there which has bad access, and somebody else can access this file and mess with the daemon and stuff like that. So private TMP means that the daemon gets its own private copy of /tmp and /var/tmp, well, whatever it writes there is not seen by other processes, and vice versa. And then when the daemon goes away, those two directories are removed. So it's not only about hiding stuff, but also about cleanup. And I mean, this protection goes both ways. So the daemon is protected from the other processes in the system and the users and so on, and the users and other processes are protected from the service. Private TMP, right? I said that the temporary directory is created, so it is created by systemd just before the daemon runs, and it's destroyed after it's stopped. And this concept is extended to other things. There's a bunch of configuration options for different types of directories that a daemon might need. So, I know, for example, runtime directory creates a runtime directory equals foo. So foo would be some name, usually named after the daemon itself or the service. We get a directory in run owned by the service. This is nice because, well, for a couple of reasons. So the directory is created right before the service runs, so we don't need to have a separate thing that creates the directory. The directory is removed after this daemon is stopped, so we don't need to clean up. The ownership and the mode of those directories is well, done properly, so they're owned by the user. Well, I wanted to make a short demo. Okay, so can you see that? Bigger? Good enough? Well, it should fit in one line. So I'm using sudo because it's a privileged operation to call systemd run. I'm giving the -t option so that the output goes to the terminal, and I'm setting property of user equals Zbyszek, so it runs as me, not as which is the default. And well, I'm giving it a runtime directory of foo, and the command I will call. So my service is just ls in this directory. So I want to show that it exists. And when I run this, I get, well, this is from systemd run itself. It's telling me that it started a service. And then this line is actually comes from ls itself. And you can see that there is a directory and it is owned by me, and it is there. If I now show this directory from here, it does not exist, right? Because it was removed when the service stopped. So the idea is that instead of having bits of configuration for this service split over multiple files and multiple scripts to create the directories and so on, you just put everything in the unit file, and it is done by systemd automatically. So this was this. I was talking about automatic creation of stuff. And what about the user itself, right? I mean, if I want to run stuff as myself or some user that I created before, that's nice. But it would be nice if we could do the Android thing, right? I mean, I need to run a script. The script should process some untrusted data. Let's use a separate user for it. And there's an option for this. It's called dynamic user. It's a fairly new thing in systemd. The implementation is pretty complex. But actually making use of this is pretty easy. So basically we just set the property. So it could be in the unit file or on the systemd run command line. And the important thing is that the user, well, I'm not specifying a user here, so it will just run as a temporary user, does not have to exist, and it is removed after the command or the service is done. So like this. Right, so it's the same, except now I'm setting dynamic user, and I'm running who am I to see what is the name of the user, and it's user RUN-U29665. So the important part is that this user name is seen by PS and other system utilities. It's not just a number, it's an actual username. If I do this again, of course, I get another temporary user and so on. So this is using this concept of creating directories on demand and removing them so that stuff does not linger after the user is gone. Because that was the trouble with creating users on normal systems, that you add the user to the database, you run some process under the user, and it might have created some files in the file system owned by this user number. And then if you remove the user number stays behind, can be added to a different user, and then this different user suddenly gets access to some files in a strange place that it shouldn't have access to. Here, parts of the file system tree are mounted when dynamic users are used. They're mounted read-only, and the user is not actually added to the user database. It is provided dynamically. So I wanted to make a short demo, which I will not actually run. I mean, this is simulating a pipeline of jobs. So I'm writing some stuff with echo, and then I'm calling grep on it, and then on the output of this I'm calling grep again and grep again. And when I run this, it will show me that I used 3 different users to just do nothing, right? Okay, so we had user separation, file system operations. What about the network? The big hammer is to disconnect the daemon from network totally. So the file system mappings, they are done using file system namespaces, and we also have network namespaces, so we can start a service where it just does not see any network interfaces or any network, and it cannot do any networking. So it's actually easier to show with a demo again. Sorry. So on this laptop, I have a bunch of network interfaces. So like the wireless WLP something interface, and the network interface, and the loopback interface, and then a bunch of stuff used for virtualization. And if I call as service, if I do the same thing, so I call IP A again to show the list of network addresses. You can see that there is only the loopback interface. So the service can talk to itself, but not to anybody else. Right. Private network equals yes is the recommended way to run network servers. Does this make sense to you? Let me check my notes. So the idea is to use socket activation, right? In socket activation, the service does not open the sockets itself; it gets the sockets from the outside. So in system, and this was what was done with inetd and xinetd for a long time, and systemd takes this to the extreme. So you can open pretty much any kind of socket. So IPv4, IPv6 sockets, TCP sockets, SCTP sockets, netlink sockets, Unix sockets, whatever, and pass them to the service. So the idea is that systemd opens the socket. For example, in the case of a web server, it could be like the HTTP and HTTPS sockets, and then starts the service. The service gets those 2 file descriptors that are the sockets, and is running in a private network, so it cannot do any kind of network operation except those that go through those sockets which are already open. So if the service is compromised, it cannot really attack the rest of the network or do any connections and so on. Yeah, socket activation, blah, blah, blah. Okay, so those options that I was talking about until now are kind of higher level options. I mean, it's all ambiguous, but the lower we go, the more options systemd has for the various things, and the ones I think that I showed up until now are kind of fairly easy to understand, even if the implementation is complicated. Easy to understand and easy to use. And now those ones that I'll be talking about now are kind of on the more complicated side. So the list is long, but just to give some ideas. Memory deny, write, execute. So writable, executable memory mappings are the stuff, and are the memory type that is used to run stuff like Java. So just-in-time compiled code where you create code, write it to memory, and then execute it. So it's a very useful thing. But it's also used by exploits, which pass some binary code over the network to a compromised server and then execute it. And most servers don't need that, so most services don't need that, so this can be disabled. Private devices is again like mount namespace operation, but kind of complex because with private devices equals yes, the service does not sees /dev with just a bunch of files. So it sees files like dev0, dev random, dev null, the pseudo terminals, and so on. But it does not see device nodes for actual hardware. So this is done using a combination of many a combination of mount namespaces and just creating some device nodes on demand. So this is useful to usually to protect against services that run as root and are, would do something that they shouldn't do. No new privileges again exposes a switch that's provided by the kernel. So once a process can set no new privileges and on itself, and when it does that, it can never escalate privileges again. So even if, for example, it calls a set user ID binary, it does not get the rights from the set. I mean, the user is not changed. So no new privileges is building blocks of many of the other stuff so that the services cannot actually escape those limitations. Restrict and the other options on this list are mostly about protecting the kernel rather than protecting the rest of the system. So the Linux kernel supports many different network families, but if you are running a web server, then it might need IPv4 and IPv6, but it probably does not need to talk Apple Talk or CAN which is for cars and so on. So we can just limit the kind of sockets it can open. Protect kernel tunables is similar to private devices. It's about hiding stuffing /proc, like all the little files that you use to communicate with configure the kernel. System call architectures. When processes on Linux can usually call system calls not just from the native architecture, so like I'm on AMD64 and I can call the AMD64 syscalls, but I can also call the x32 syscalls and the 32-bit Intel syscalls and so on. And calling those foreign syscalls is often not implemented perfectly by the kernel because it's pretty hard to do. The memory sizes are different and there needs to be some translation. So by forbidding those foreign syscalls from being called limits the exposure of the kernel. I mean, it is possible to assign a specific list of families, but the most typical use is just to say native, which means that whatever the architecture that this service is running on, it can only call syscalls from this architecture. And log personality is about forbidding personality changes. So the kernel can pretend that it's a different thing, and then some stuff happens slightly different. It's a very niche thing, again, something that can be turned off. And there's a bunch of other stuff like that. As I said, running as an unprivileged user is the perfect option, but sometimes it's not possible. But the Linux kernel has this concept of capability, so it's taking the root user and kind of splitting it into different parts. So we might have a service which, for example, needs to mount stuff, but it should not configure the network, and then we can, or it should not do time operation, or the opposite. An NTP daemon should be able to set the time, but it should not do any kind of other privilege operations. So there's a bunch of options to set which capabilities are given to a service running as root. So there's a problem how capabilities interact with capabilities set on files using extended attributes. So ambient capabilities are a way to work around this. This is all wrapping functionality provided by the kernel. Okay. And this is also row level, but it's pretty interesting. So the kernel provides an ability to attach a short program to any program, which will filter which system calls this program that is being contained can call. In other words, I mean, it's we just set a filter on the syscalls. So this was initially used by Chrome, the browser, to when it was running various plugins, it would just limit the operations the syscalls it can call. So, for example, a plugin should be able to call read and write and do some memory operations and stuff like that, but it shouldn't be able to open files or do any kind of other file system operations or network operations and so on. So we write a filter that allows just a few syscalls and not the rest. And in systemd, this is called syscall filter. You provide a whitelist and a blacklist of syscalls that are allowed. This is implemented using libsecomp. So the syntax is basically that you give just a bunch of names. They can be prefixed with a tilde sign so that you get a blacklist, and without you get a whitelist entry. But there's many system calls. So there's this syntax with add. It's about groups of system calls. So, for example, basic I/O is about basic reading and writing to the file. So if you want to allow write operations, then you probably want to allow similar operations like write v and so on. And if you want to allow fork, exec v, then you want to allow the similar variants and so on, because it doesn't really make sense to filter for a specific one. And also which syscalls are available between architectures varies. So we provide those groups of add groups that let me show this so you can hold this with you. So basically, there's like the default group that contains a bunch of stuff that it's used by the by a process to do its normal operations that is required for pretty much everything. So this is allowed by default, and then there's basic I/O for basic operations on file descriptors, and then those groups can be mapped into other groups and so on. And then there's, for example, group obsolete. So those are old and strange system calls. I don't know if anybody knows what this one does, tax call. So for people born, let's say after the 90s, it's a syscall for the built-in web server when Linux was competing with Windows NT, I believe. This isn't actually implemented anymore, but it's still, you can still call it. You will always get an error for compatibility. So, for example, you can forbid just blacklist everything in the obsolete group, and this just limits the attack surface that the kernel exposes. And I should mention that the command that I was using to show this, it's a command line thing, because this list varies over time, and systemd versions add and remove syscalls as we learn what should be added and removed, kind of keeping the spirit of different groups constant. Okay, and so this is also kind of low level but useful. So systemd implements, or rather I would say exposes a firewall which is allowed by the kernel to be attached per control group. So under systemd the services run as control groups, and the kernel with control groups version 2 allows a filtering program to be attached to any control group, and then it can. I mean, the kernel has support for a lot of stuff, but systemd currently only allows a few things. IP address allow and IP address deny is about creating a whitelist and blacklist of IP addresses. So this supports IPv4 and IPv6 just for processes of the service. So this is not a part of the firewall. The big firewall that protects the whole machine is attached to this specific service. And on this one, it can communicate with this network and this IP address, and everything else is forbidden. So that's the stuff that is implemented that I want to talk about. And there's some things that are being implemented currently. So more of the firewall stuff. There's a pull request that has been under review for a couple of months to allow filtering on ports. So the idea is that, for example, you have a web service which should just use a few ports and everything else can be forbidden and so on. To kind of convince people to use those features more, we are providing we will be providing a way to display a status report with colors and emoticons, so people enjoy using it. So basically the idea is that you, I'm calling not the real systemd analyze binary, but the one from my build directory, security, and then give it the name of a service, and then it will give a checklist of stuff that the service is doing right, and the stuff that the service could be doing in addition. So I don't know, this one is not using private network, but it's using a user, and I don't know. It has some settings set, some settings not set. For each one that is not being used, as there's you get a badness score, and in the end this is summed up. It says that the service is doing kind of okay, but could be doing better. It's a sum of 5.4. So this will probably appear in systemd 240 when it is released in a few weeks. And that's more or less it. I would say that we have an active bug tracker, and if you can see from the statistics provided by GitHub, if you file a request for enhancement, there's like a 50% chance that it will be unimplemented but not closed, and a 50% chance that it will be closed, so either implemented or rejected. But please file issues if you find bugs in systemd, and please file requests, RFEs if there's some stuff that should be there but it's not. And I still have some time for questions, so if there are any.
So how much all this stuff is built on top of the Linux, and how much is like re-implementation of Linux? Because there is a lot of stuff that for me is a mix of the features provided by Linux and the regular features of kernel, like capabilities, namespaces, file namespaces. How much and how does systemd cooperate with Linux when there is a different policy in Linux and different settings in systemd?
Yeah. So the question is how much of this is implementation of Linux and how much it uses Linux and how systemd cooperates with Linux. So systemd has explicit support for Linux, but it's not used by any of the options I mentioned here. I mean, it understands Linux and can set Linux context and can do Linux checks, but this is separate. So all those features that they are using other stuff provided by the kernel. And apart from Linux, we have direct support for SMAC and AppArmor and some other stuff like that, I think. So basically the answer is that all this can be used in addition to Linux. So Linux will provide additional filtering on top of all that. So usually it's like, all those operations are about removing things that you would be able to do otherwise, but if other stuff forbids it, it's almost never about adding capabilities that wouldn't be there otherwise, right? So it's only about, each step is about removing some more stuff.
Yeah, but how it would work with like dynamic users if there is a strict policy in Linux?
Well, it works. I mean, there is a policy added in Linux that in Fedora 29 that somehow makes it work. I'm not a Linux expert, so I don't know. But
okay, thank you.
So no new kernel privileges causes an issue with Linux. So there are sometimes some conflicts, but there are not so many, and they're being worked on.
You mentioned that some features may not work without processor support. Can you give a concrete example?
Yeah, it's not really. Okay, memory deny, write execute does not work on 32-bit Intel, depending on the kernel. But actually, this is more about. So many of those things use seccomp, and if, for example, seccomp is not available for a given architecture and the system call filters, then we won't do filtering there because it's not implemented. So it's more about us not having support or other libraries not having support for a given architecture than about the architecture itself. There's few things that are really architecture specific. And there are some examples like syscalls. So the socket operations on 32-bit Intel, they're multiplexed using a single syscall. It's kind of hard to filter that. And on other architectures, you have this one syscall is split into multiple ones, so you can do proper filtering of operations. And then, so on 32-bit Intel, you don't get full support for this. Okay,
one more question. Okay. All of this stuff can be used with the system and spawn, and for whatever crap we want to run as a container, like and spawn container.
So the question was whether this can be used with nspawn. So the problem with nspawn is that when nspawn is setting up the container runtime, it needs a lot of privileges. So nspawn itself has a lot of support for doing confinement, but if you confine nspawn itself, that's not really useful because it needs very many privileges to do its setup. I mean, it needs to do all kinds of namespace operations on all namespace clients and so on. So, and it's just the wrong place to do it in this case. Okay, thank you.